we'll make this the y-axis. On the XY plane, it has a surface current density K equals 2 pi AY.
In the what? AY? Okay, so they have a surface current density, K equals 2 pi AY, and that would be amps per meter. Go ahead.
Determine the magnetic field intensity at the point A, P, which is 0, 0, 2 centimeters, and then B, which is part B, Q, which is 2 centimeters, 2 centimeters, 2 centimeters.
All right, so for the first one, they want it right up the z-axis 2 centimeters, right?
Yep.
And for the second one, they want it
2, 2, 2.
So then it's going to be 2 here, that doesn't matter in the y because it's infinite. So it's 2 here, and then 2 here, so here, all right? Now, when you're doing this is one of these building block approaches. We've got the actual H field from an infinite line of current. Do y'all remember that? Everybody? We developed that. So I'm going to just put that here. We know if we have an infinite line of current, and I'll call it, it doesn't matter this direction, for now Z, and I'll explain in a second. And we have a current I. Then I know if I come out a radial distance rho from here, I'm going to get an H field. And that H would be in the phi direction. That would be I dl cross A rho over 4 pi, over 2 pi, and it's divided by magnitude of rho. Now, I'm doing this for a reason this way. You're used to seeing just A phi here, right? But really, if it's not on the z-axis, if the current is on the z-axis, then you need to get the direction doing the cross product there. Does everybody follow me on this? Now, what I'm going to do, that's generally true if we have a given current. If we had a thin filament of current or something with a thickness like so, or now this has a thickness of d rho, in this case the thickness would be dx, then instead of I, what we'd have is the surface current density K times d rho would be equivalent to I. Does that make sense to everybody? Now we're just going to take, remember K is amps per meter. If we multiply by meters, we get amps. So we're going to have a sliver of current right there, and we're going to get the H field, but now it'll be the DH field. So let me go from here, and I'll say the differential H field, and I'm not even going to say it's the phi direction anymore, would be equal to K times d rho, and there's a vector sense to this since AZ here, over 2 pi rho, and rho again is this distance, the perpendicular distance, AZ crossed into A rho. And remember, A rho is a unit vector from the center point of that current filament to the point of observation of the H field, correct? Everybody? Just follow me on this one. First, you have to establish that you've got to accept that as the truth. Then we're going to modify it to go ahead and take care of that. And I call it the building block approach because this is your building block. This is the thing we know that we can use to get the H field for that. Now, the hard way to do it is just take a differential chunk of current here and then say this IDL, right? IDL crossed into AR over 4 pi R squared would be equal to DH, and then you'd have a double integral. You could do it that way, but it's more work. We've already did one part of the integral. You follow me? You get this. Now I take this and I apply it to that particular problem right there. All right. Now I'm going to say that therefore the differential H field at a point, and let's do it at a point X, Y doesn't matter because it's infinite in the Y direction. So it doesn't matter, you can call it 1 in Z. So at any point, X, Z. Anyway, all right? Now, follow me in this class? When we do this, it would still be that K, and then instead of D rho, it would be DX. And this is in the AY direction, so the unit vector would be AY associated with the surface current. And I'm leaving it as K. I know it's whatever the value is, 2 pi. All right, but forget about that for now. I take that over 2 pi, and now I'm going to get rho. So what I have to say is if I have a line of current, I mean, it doesn't have to be at the center. If I have a differential chunk of current, right? And I'm taking it and I'm trying to, it's gonna be hard to follow me because of the drawing. This is actually dy thickness, right? There's my differential sliver of current that I try to show there. And now I need to find this radius vector, rho, to the point of observation. I'm just gonna put it this way, and this is rho. So what is rho? Well, rho, I've gotta say that this is gonna be at a point y, right here, follow me? And we'll call it, why don't I call these prime coordinates? I'm sorry, in a point x, my bad. Because this is x, this axis, and I'm shifting it, y is up and down. I'm moving this, the x could be at 0, it could be at -1 centimeter. Follow me on this, class? Everybody? All right. I'm gonna use these as prime coordinates and I'll call that x. So when we look at rho, first it's the position of observation of the field. Let me make this a little clearer. I'm gonna say that my rho vector from this goes to a point, that is the x-axis. It's gonna go to a point of observation where I want the h field, or I want dh. And this dh is at a point x prime, 0, y prime. So that means rho prime would be x prime minus x, ax. Do you follow me? I'm gonna do this in Cartesian. Everybody? Follow me? At the point of observation is x prime. I'm calling it x prime. The source point is at x. That's where the line current exists, all right? Then it's gonna be, y doesn't matter in this one. You can put any y you want, but really, just forget that, and now you need the z distance. Well, the z distance would be what? Point of observation, I put a y prime, it should be a z prime. Sorry about that. Actually, it can be just z. That can be just z, we don't need to prime that one. Do y'all follow me what I'm doing? I'm trying to get the distance between this current, this thin current slit that's located at x, right? Whatever value of x is, and then at 0 in the z direction, and it's infinite in y, correct, class? Everybody see this? So when I do this, what's the coordinate of point of observation in terms of z? Just z, right? It's z. Minus 0, or just z, a, z. So that's my rho prime, right? Now, that's rho. Now, magnitude of rho, of course, would be equal to simply the square root of x prime minus x squared plus z squared. And then my unit vector a rho is simply equal to rho prime over rho magnitude. And, yeah. All right, now we take this, so I have k dx ay over 2 pi. Now I have to put rho in here, which is this, but I'm going to leave it as quantity x prime minus x squared plus z squared, and it was to the 1/2 power. I'm going to leave it as 1/2. Then I have to cross this with a rho, and a rho would be rho prime, which is x minus x, x prime minus x ax plus z az. And I have to divide it by magnitude, so that gets rid of that 1/2. Everybody follow what I did here? I'm just taking what I put over there and inputting it into the equation. So it's I, and I becomes k dx ay, and it's crossed into a unit vector, a rho, and that unit vector is really this divided by its magnitude over 2 pi rho. So this becomes, instead of having a square root, it's just to that first power there. Everybody agree? Follow me on this one, everyone? Now, I don't know how he sets it up in the book, but this is it's a good problem, right? It's a good problem because it teaches you how to think using what I term the building block approach to solve a problem without starting from scratch with a differential chunk of surface current. Then it becomes harder because you've got to solve 2 integrals. Here, I think we're only going to have just one fundamental integral after this. So when we take a look at this and we do the cross product, I want to show you that the k over 2 pi comes out in front. So what I'm going to say is for dh, we know we're going to integrate this. I have k over 2 pi out in front. And by the way, since k is 2 pi, that basically goes to 1. Yeah.
Where did the square root go on the bottom?
Well, remember, it was square root here when it was rho, right?
Yeah.
But then when we had a rho, what is a rho? It's rho over magnitude of rho. So that's a square root of all this too, right?
Yeah.
Square root times square root is just the first power.
Okay.
And so it becomes the first power. And then, here's what happens. Now I have this. I have ay dx crossed into ax. Ay crossed ax is?
Minus AC.
That's right, minus az. So it's going to be minus az here. And it will be the integral of, that's going to be x prime minus x dx over quantity x prime minus x squared plus z squared. That's the first part. And then we have, yeah, that's right. Then we have ay cross az, which is yz ax, right? Plus ax times the integral, and here we're going to have z over the quantity x prime minus x squared plus z squared. And that would be dx as well. And where does x go from? It's 4 centimeters in dimensionally, but is it centered on the y-axis, class? All right, so it's from minus 2 centimeters to plus 2, right? So we'll just put these integrals. They both go from, how about if I say from minus 2 centimeters to plus 2 centimeters? Everybody agree with that? Now that's the differential, I'm sorry, I set it up as an integral, so that will be the H field anywhere, correct, class? Now, the real thing here is, try to simplify it as much as possible. You'll notice Dr. Wentworth chose k as 2 pi. So 2 pi over 2 pi is 1. First thing I do is eliminate this, right? Now the next thing when I look at these integrations, I'm going to do them, if I have x prime minus x over x squared, over that squared plus z squared, obviously the simple thing to do is make the variable, well, you can do this in either way actually. I think, let me just try this. First, I'm going to say that really this looks like, if we say, try to do this the easiest way. Yeah, I think we can do it this way. If I say u is equal to x prime minus x squared plus z squared, then du dx, right, or dx right here, would be equal to 2 times x prime minus x, and then the derivative of this with respect to x would be minus, just minus dx here. So that would be du, and you can take a look that I could do this for this part of the integral right here. I can say the integration from x goes to minus 2 centimeters to 2 centimeters of here, the x minus x prime here, x minus x prime is minus du over 2. So I have minus du over 2. And then I have divided by this, which is just u. That's this integral right here. Then I could put the minus az in front of it. And the only reason I'm doing that is then, this is what I'm doing first. Once I put the minus az, I can see that the minus signs cancel. Y'all see that, class? Now, at that point, this integration is what? That becomes simply az divided by 2, and then it's natural log of u, right? And here, the limits on this, Well, if u is equal to this, follow me, when x is equal to minus 2 centimeters, right here, then this becomes x prime, this would mean u is x prime minus, or plus 2 centimeters, 2 times 10 to the minus 2, squared plus z squared. That's what the lower limit is, and the upper limit would be u equals to x prime plus 2 times 10 to the minus 2 squared plus z squared. So this would be lower, and this would be upper limits on this evaluation of the log. Do y'all agree with that, class? Remember, I made the substitution for u, right? So the limits of the integration have to reflect that. Since x was minus 2 centimeters, I have to put minus 2 centimeters in there for x, right? And that makes it x prime plus 2. Now remember, the x prime and the z are just the coordinates of the point of observation, which we plug in at the end. So that's the first part. And I guess I can do this. I can say that's az over 2 times natural log, I don't like doing it this way, x prime plus, how about we do it, 0.02 squared plus z squared over, and this would be, actually that's minus right there, isn't it? Is that right? No.
Yeah, minus is right.
Yeah, this should be a minus, and this should be x prime plus 0.02 squared plus z squared. And that's the first part of the integration, right there. The second part, right over here. Does he do it this way in the book, by the way? I mean, the solutions?
No.
What does he do?
He takes a formula and plugs in the numbers.
The formula.
Yeah, he starts with this formula, which I think he does a page before this with the trig substitution.
Oh, he does the problems. That's the whole thing. He does what we're doing right now. And he does it, yeah, just like we're doing. He has R and all that. All right, then here, for this integration, take a look at it for a second. That integration is, hey, did I mess that up? X minus AZ, Y, Z, it's 8X. This is 8X here. That's AX. So then for the second part that I circled there, now the integration, it's AX, integration of Z over X prime minus X squared plus Z squared dx. Here, X goes from minus 2 centimeters to 2 centimeters. On this one, problem is I gotta get a differential. If I make u squared equal to x prime minus x squared plus z squared, then 2u du would be 2x prime dx prime. What's that? Pardon? Look, what I'd like to have is an integral where it would be dx or du over like u squared. You follow me? I'd like something like that, or u. The problem is, there's probably an easy way to do this, but if I look at the bottom and I say u squared is equal to x prime minus x squared plus z squared, then du dx, right, would be equal to Then when I take a derivative of both sides, I get 2 times u du dx would be equal to 2 times x prime minus x. And then if I multiply by dx, I get this, right? Well, let me see here for a second. Maybe I do have it. So that becomes du would be x prime minus x dx over u, which is square root of x prime minus x squared plus c squared. And that would be d, that's du. And so dx would be equal to square root of, I don't want to waste too much time on this.
I think he just uses like a trig substitution.
You can do, yeah, when the one I'm thinking of, since this looks like a sign substitution where we have opposite, but the problem is that's not a square root here.
Right.
So what you'd have to do is like a secant substitute. I think it would be a either tan
Tangent is what he
Arc.
uses.
or tan, yeah. What's the answer for this? I mean, this integral right here. He makes this thing the arctan. I mean, he makes that. I'm not going to waste time. Do you have the answer to this one?
Yeah, it comes out to negative k over pi.
No, K's gone. I just want this answer to this integration.
Oh, he doesn't list it, he just skips to the very end.
Real quick. If we let x prime minus x be equal to tangent theta, then when I had minus dx, that would be secant squared, that would be equal to secant squared theta d theta. And then this integral would become ax, and it would be the integral, the z comes out front, that's no consequence. And dx here would become minus secant squared of theta d theta over, and this would be tan of theta squared plus z squared. And the problem is that's not a 1 there. If it was a 1, then I could do a secant squared substitution here.
You make x prime minus x equals to.
What's that?
If you make x prime minus x equals to c tangent.
Yeah, you're right. And if that's z tangent, then that would be z, right? And then I could factor out that. And if that's the case,
You just end up with d theta.
well, there's a z up here, right? Hey, wait a second. There's a z there. I'm sorry. What would you say?
I say you would end up with just d theta.
There would be a z here and a secant, and then this would bring a z outside, right? And that would become 1 plus tan squared is secant squared, isn't it? But something's up with this because that goes to 1.
Yep, then it will be arctangent when you put theta.
When you do the limits.
Yes, sir. I mean, it will be just theta,
Substitutions.
and then it will be arctangent.
Yeah.
Back to the substitution.
This goes away, that z and that goes away, and I'm left with d theta, right?
Yes, sir.
Integrated, and so I have minus z ax, and then that would be Now when I put in this, let's see, when I put in x here, it would be x prime minus x over z inverse tan of that. So I'm gonna just go ahead and say that this is gonna be equal to minus z ax, and it's gonna be tan minus 1 of, and then that's going to be x prime minus x divided by z that's ax here, and it's going to be minus tan minus 1 of x prime minus x over z. But I have to put in the values for x. X right here is minus 2, so that's plus 2 centimeters. And that's that's going to be a minus, and that's going to be a plus 0.02 over z, and that would be the answer for that portion of h right here. So you'd have to calculate this and then this, and that should give you the right answer. Is that what he does as far as the formula in the book? Does he have one with an arctan and one with a log?
You have one for, there's only an x component, I think, that one, yeah.
No, that's only if it's right on above. It's only going to be an x component if it's right at the center.
That's the one that he has, so that one is right.
All right, but the other one, doesn't he have one where it's on the edge?
I think on the solution, you just evaluate the interval using numerical index.
Oh, that was nice of him. Well, this is how you do it. You plug in the values here to do that. But I'm going to tell you some of the integrals, and I don't do these very often. Most of these, if you work with them for a while, you'll know the substitutions. But frankly, your calculators do symbolic integration. I think they can give you a symbolic answer, can't they? If you plugged it in, you'll get an answer for that. And so that's what I'd recommend doing. Anyway, if you want me to, we can evaluate it, but that's too much time on this already. Is that all right? Now, some people are going to ask me, would I ask you that problem? I wouldn't ask you that problem unless I give you some formula for the actual entire strip thing like he does. But one thing I will ask, and I do at times, I'll ask you to set up the integrations, but not evaluate them, so I can check and see if you know what you're doing. Because a lot of times people don't know how to construct the final integration based on like the known solution for a line, an infinite line of current. So that's the long and short of this one. What's the next? Any other problems? It's a good problem.
411.
Which one is that?
Solenoid.
Did we do the loop in class last time or not?
Yeah. Or
They just
Yeah,
started.
we did.
we started.
I think I gave you the answer quickly, didn't I?
Yeah.
Let me just go through this. You don't have to write this down, but I want to make sure everybody is on the same page with this one. Whenever you're doing these things, like solenoids or toroids or anything, you always look for some solution that you have done in the past that could be used to get a segment of that thing, to find a solution to just a portion of that, like a differential, like I just did. So for this one, if you have a solenoid, or I'm sorry, if you have a ring of current I here, and let's make the radius, I'm going to make this radius rho, because I know I'm going to have a variable, well, I could make it A, but I'm going to leave it as rho. And I'm going to say I want the H field at the point Z here, so I'm looking for H at this point at a height Z. Think of it this way, this is height Z. And the ring is centered in the XY plane. So the way you set up the problem, and this is the way you always set it up, you first find the differential amount of current. So that's equal to I dl here. I is a constant. dl, and remember this in cylindrical coordinates, dl is going to be this differential distance, which is really going to be d phi times rho. A lot of people mess that up. So it's going to be rho d phi, and the direction for the current is, if we're in cylindrical coordinates class, a phi, right? It's circulating, so it's a phi. Now that I have that, I can get the differential H field, and that's equal to I dl crossed into AR over 4 pi r squared. Here, we can say R vector, and that goes from this point to this point. So if we look at R vector, we can say, we'll do this in cylindrical. Well, the difference in radial, it would be 0 minus rho, right? So it's minus rho, a rho, and phi you throw out. Don't even worry about it because we're right on the z-axis. Phi has no meaning there. You follow me on this, class? There's no interpretable meaning for that. So throw out phi, and then for z, it's plus z a z. Does everybody agree with that? Right. We have that. Now, we'd say the unit vector AR is simply R vector over magnitude of R, which is just the square root of rho squared plus z squared. So now that I have all that, I construct this and execute the integration. And I know my dH would be equal to I dl, which would be I rho d phi a phi. And that's going to be crossed into a rho, and I'll put that in a second, over 4 pi r squared, and r squared is just rho squared plus z squared, because it's, if this is r, the magnitude is square root of rho squared plus z squared. Squaring that would bring this out, and it's crossed into a rho, which is going to be minus rho a rho plus z a z over the square root of rho squared plus z squared, or make this to the 3/2 power, and that would be the differential H field. Does everybody agree with that? We did this last time. Then we have to integrate this to get the total H field. Where do we integrate it from, class?
0 to 2 pi.
Right, make sure you 0 to 2 pi. I'll say one other thing too. I know people may not like doing it because it's 8 o'clock. The more interaction you get in verbalized answers, the military knows this very well, the more likely you are to retain the knowledge. Just remember that. I don't do this just to hear things. I try to encourage you to do that for your own sakes, because I know that works. Sometimes you don't like doing it, especially when you're tired, but it works. Now we're going to go ahead and do the cross product on this stuff right here. When I take a look at this, what is a phi crossed a rho? And here's how cylindrical coordinates are always rendered. It's rho, comma, phi, comma, z. And the way you think of it, if you're going this way, from left to right or back here, that's all positive. If you're going this way, it's all negative as far as crossings. So if you look at this, I have a phi crossed a rho, which would be minus az. And because there's a minus sign, I can make that plus az. I'll get rid of that a phi in a second. I'll get rid of that in a second. What about a phi az? Plus a rho. Get rid of the cross. Now that's the integration you have to accomplish. And here's where I make the statement about symmetry. And I did it last time. I could prove this by going ahead and saying that a rho is really equal to, unit vector a rho would be cosine of phi ax plus sine phi ay, and then do the integrations with respect to phi, and you would see both of those integrate out to 0, because the integral of a sine or a cosine from 0 to 2 pi, where the argument stated, is 0. But I'm not even going to bother. What I'm going to do is say if I have a differential current IDL here and I go right through to the opposite side, called the conjugate point, or 180 degrees around the circle, I will have the same current's magnitude in the opposite direction, and it will give me an H. This will have an H component this way, this way, and the horizontal components will kill themselves off. That's my contention, and it's true. I used to go ahead and prove that, but today I don't think we need that. So really, this is the integration I'm left with, and you are. Please take a look at this for 1 second. People, as soon as they get an integration, where they got something like this, they think they actually have to do an integration with respect to zero rho, and look carefully. It's only an integration, integrated phi, right? Well, nothing in here except d phi varies with phi, so everything's an apparent constant. Does everybody see that? Everything, there's nothing inside here except for d phi that has a phi component. So therefore, when we do the integration, we're just multiplying by 2 pi, right? Integrate d phi, you get phi. From 0 to 2 pi is 2 pi. When I plug in 2 pi times this, there's a 4 pi here, so it makes this simply 2, right? And that's my answer right there. And you can see that you get a rho squared here. And that's the answer he has in the book. Something to note about this. What is the value of the H field when Z is 0? It's what? I over 2 rho, right? Isn't it? I over 2 rho. You'll notice it's not 0. Remember when we had a ring of charge and we looked at the E field at Z equals 0, it was 0. The other thing about the E field is when you went below, if this was a ring of charge, when you went below where Z equals 0, it became negative. It inverted the sign, right? Here the sign always is the same. H field is always going to have, in this case, a positive sense. If the current is swirling in the counterclockwise direction looking down the z-axis. So keep that in mind. Now we have that. And we use this as our building block for the solenoid. Is a solenoid centered on the z-axis of some length L?
Yeah.
Okay. I'm going to try to set this up. Solenoids are interesting. Now I'm going to assume that this has a radius rho. Doesn't matter what the radius is. And this is the z-axis, right? And I'm going to assume this is going to be L over 2, the height, and this would be minus L over 2. So I'm centering this right on the z-axis, so half below, half above z equals 0. And then this is the origin, right? And now what I'm going to do is say that I have a ring. I'm going to have this a differentially thick ring at a height z. And I'm going to have this ring that I probably can't draw very well, but you can follow me. An infinitely thin ring like this around here. And this is going to have a thickness of dz. Can you all see what I'm doing there? Now remember, a solenoid's just a whole bunch of wires wrapped in a circle, tight wrap, right? And they usually give it in terms of turns. They'll have n turns, right? And over a length L. So that means the actual surface current density, K, would be, if you think about this now, suppose we have n turns in the solenoid. I'm trying not to make this too messy, but there's a whole bunch of wires that are all wrapped, right? And there's n turns there, over a total length L. Now each turn carries a current I. Follow me on this? Well, how much total current is swirling around? The total current would be n times I. Agree? But now you want a current density, a surface current density, so we divide that by the length, and that is by the length, and put a vector there. It is in the a phi direction, and that would have the units amps per meter. So that's how much current per meter is swirling. Does that make sense to everybody? N times I is the total current. If you divide it by L, you get the current density. And that's the amount of current amps per meter height of this. Okay? Now what I'm going to do is say, I'm going to reduce that problem even further. I'm going to try to make this something that everybody can understand. So if I look at this, and this is my ring, and I cut it in half, really what I have is I have a chunk of current right here that is dz thick. It has a current density K, and it's at a height displaced from the axis z, right? Now, does he want the H field at the origin or not? This is not done very well.
Yes.
Just at the origin? Okay. So if this is minus L over 2, and the top here is L over 2, I want you to follow me. I know here at the origin, I can get DH. And you gotta keep in mind that we still have to get vector R here. So when I look at this, this has a radius of rho, height of Z, and I can say that R vector would be point, again, coordinate of observation minus this coordinate. So with respect to rho, it's going to be minus rho A rho. And with respect to Z, it's plus Z A Z. Y'all agree with me there? Right, now, when I say I need a R here, or a rho, it would be equal to simply R vector over magnitude of R. And then when I get the differential H field here, at the center, I go ahead and I take this approach. I'm going to use this form of equation, but instead of I'm going to say that this is going to be a differential H field, and I will be equal to now K dz. Does this make sense to everybody? Now I'm going to take, this is dz thick, so the amount of current in this thin ring would be K times dz. That would be di would be equal to K dz. Make sense to everybody? Are you with me? If you looked at this problem, this should make perfect sense. We started with a ring. We're going to get the H field from a ring of current. Now, we have a ring of current, but it's infinitesimally thin, so it has a differential amount of current, not a given current I. And now we're going to get the differential field from that. So now the differential H field would be I, or it would be K dz, and it is in the A phi direction, right? Actually, we can just use this and not even bother with the cross product, because that is the final form. And it would be in the AZ direction. AZ. It's over 2, and then this is rho squared plus Z squared to the 3/2 power, right? And that's the differential H field. Do you agree with me? And I mean, I have to put the rho squared here too. There's this rho squared I have to put in. But that would be the differential H field. And K, of course, I'm only using magnitude of K, whatever K is the Ni over L. Follow me? But I'm not even going to put the Ni over L until the end. Now when I do this, I have to integrate it to solve it, correct? And I'm going to have to integrate this from minus L over 2 to L over 2 to get the total value of the H field. And therefore, the H field at the origin, I'll take out the constants. I have K over 2. And then I have the AZ. Since the integration is Z, I can also take the rho squared out in front. And I'm left with the integral of dz over rho squared plus Z squared to the 3/2 power from minus L over 2 to L over 2. Right? Now we have to evaluate that integration, and unfortunately I don't have a Z here, or I could get a complete differential. This is going to come out to be a 1 over the square root of rho squared plus Z squared when all is said and done with that. So this integral's in the back of his book. I'm trying to think of the easy way to do that one. I can tell you right now that this will come down to, it'll be 1 over the square root of rho squared plus Z squared, plugged at the limits if you look. You can take a look at that, but I'm trying to think of a quick way to do this. What's that?
I think it should be Z over rho squared, square root of rho squared plus Z squared. I mean, I think when you integrate it, that's what you end up with.
Oh, the Z comes out. That could be.
Yeah,
Yeah,
that's
that-
the one in the back of his book.
Let me see that. there, and that z would come out, and it would have over that a squared, which would be rho squared. So this would be equal to, Duncan, stay there for a second on that page, k over 2 az, and then it would be, there's rho squared there. Then when you do this integration, you're going to get a z out in front over the rho squared, and then you're gonna have 1 over the square root of rho squared plus z squared, right? And that, to the 1/2 power, that has to be evaluated at z equals minus L over 2 to z equals L over 2, correct? There's a z and a rho squared that comes out, because he has a squared in his book for that integration. And this should be it, but you're gonna notice one thing. What happened to the rho squareds?
Cancel.
They go away. So then when we plug this in, if you want it the whole 9 yards, you can plug this in, but what do you really get? You get kz over 2az, and then you get 1 over a rho squared plus L over 2 squared. Wait a second. Oh, there's a z here, never mind. You get L over 2 times the quantity 1 over rho squared plus L over 2 squared, and then you get minus z, but it's minus minus or plus z times 1 over rho squared plus z squared. So this is going to come down and have a form of, it looks like k over 2 az, and then you're going to have L over 2, and then it's going to be 2 divided by square root of rho squared plus L squared over 4. And that should be the final answer. The 2's will cancel. Is that the answer he has in his book? And then you plug in k as ni. K here would be ni over L. And that should be the H field. Does he have this in the book as the answer? Ni over L divided by 2. Oh, the L's go away too, I think. Wait a second. No, I take it back, they don't. It should be Ni over L divided by 2 times 1 over the square root of rho squared plus L squared over 4. Does he have that?
He has an L on top still.
Oh, weird. There's a 1 over L. There should be there should be L and a 1 over L, right?
Yeah.
But they cancel, don't they?
Yeah, they would.
All right. I think I had that there. Is this what he has right here? All right, it's one of those ones that, it's the building block approach to get that answer. Was there any other problems? And if you're asking me if I'm gonna ask you to do a complete integration like that, I probably would ask you to do something where the integration, I'd give you a table if I asked you to do something where you need to evaluate an integration. It's one of the less common ones, all right? I'm not gonna ask you to memorize all the secant squared substitutions or tangent squared substitutions and all that. I'm just gonna ask you to, be aware of how to look at an integral table or use your calculators because you have symbolic integration, all right? Any other questions about the homework? I gave you that homework not covering the solenoid, not covering the strip, with the thought in the back of my brain, it would beg the natural question that I could answer in class today. When you try to do the problems and you look at the solutions, you're gonna have questions, and when you come to class with questions in your head and their answers, it sticks with you a lot, instead of just introduce a topic and kind of casually go through it. There's one thing we haven't covered, and that's the infinite sheet that you mentioned is the one. Now, to do the infinite sheet, how would you do it? Just think about the problem we did earlier. Didn't we do a finite thickness sheet or finite width sheet, right? Well, just let the limits of that go to infinity, right? And then we can evaluate it. And we'll do it right now. Does anybody get their breakfast at Chick-fil-A here? You do? How long does it take?
Like after class, if you were to go?
Oh, no, I'm talking about before 8, because I mean, that line coming out of there, and I'm not exaggerating, there's 30 cars there at least.
Oh, yeah, I never drive or anything, just walking, it doesn't take too long.
Well, I'm gonna guess it's 20 minutes at least for those guys.
Yeah.
Easy.
Walking is way faster.
What's that?
Walking is way faster, yeah.
I'll remember that, if I ever wanna go there. Still kinda mad at the jam traffic. All right, the next thing I'm gonna do is show you this infinite sheet. Now, when you take a look at this, we did this problem for the finite dimensions. If it's an actual infinite sheet, I'm gonna try to draw this. If you have an infinite sheet of current, that means, try to draw this, assume it's in the XY plane. So this would be X, this is Y, and I'm gonna say the current sheet has a vector current K in this direction. And since that would be minus AX, so call it K is some magnitude of K in the minus AX direction. So it's going that way. All the current is going this way, like so. And we let this become infinite. So assume it goes forever. What actually happens is, when you take that, if you're above the plane, if you're up here, that what'll happen to the H field above there, well, will be that you will get an H field parallel to this plane. So if this is X and Y, the H field will be in the plus Y direction, and its magnitude will just be K over 2. And he always does, let me make this a little more clear. Above the plane, let me put it well above the plane. If you're above the plane, the value of H for my geometry, if all the current's going that way, will be equal to K, the surface current density, over 2, and it's always given as this, it's K vector over 2 crossed into A normal. This is the way his book will have it. And if you evaluate the integration, this is what falls out of the integration when you take the limits to go to infinity. Now, in his book, I just want to give you the page number where he has this in his book. He doesn't show the infinite sheet until he goes into Ampere's law. We're going to get there today. He has it on page 226. I'm sorry, 227. It's formula 417, if you look there. Now, for ours right here, the way I've drawn it, what this will be equal to, K is minus AX. A normal is a vector normal to the surface where the sheet current exists. So a normal is always pointed away towards the point of observation. In this case, the normal would be AZ. Do you agree? So if I put this in here, I'd have magnitude of K, whatever that is, and that's in the minus AX direction. Crossed into AZ would be my normal, divided by 2. You can see I would get magnitude of K divided by 2, and AZ, or AX crossed AZ would be minus AY with a minus sign is plus AY. So that's what the H field would be above. But below the plane, the H field will have the same magnitude, only opposite direction. Here the H field would be equal to minus magnitude of K times AY over 2. It's going in the opposite direction because the normal vector is now pointing in the negative direction. Does everybody see that? Follow me? If you just take that formula, K cross A normal over 2, K is still in the same direction. It's magnitude of K minus AX, but now A normal would be minus AZ. With me? And this is the formula. This is the thing you remember. Now, there's one really important thing to catch from this. We're assuming it's an infinite sheet with a surface current density K. Well, if I talk about proportionality here, if I'm going to say I have a constant current density, surface current density is so many amps per meter from that wall right there, the base where the carpet hits the wall, to say the front row of seats, and I'm this high above it, that doesn't really look infinite. I would have to default to the formula given for a strip of current to calculate the H field. But if I'm a millimeter above that surface, to me it looks infinite, because on the horizon it looks like I'd have to go out almost to infinity to see the horizon point there, or 90 degrees. When you open up, if you look, it's about 90 degrees out. And that's that's sort of the way you do business. If you want to know if it's infinite, and you can, in your mind, place yourself at the point of observation, if you have to look up from looking straight down by 90 degrees to see the horizon where it ends, then it's infinite. That's sort of the way they talk about it. Anything close to that. There's something else though. If it's infinite, what do you notice about K's value versus how going away from that, if it's infinite? I mean, not K, but H's value. What happens to H if I go 10 miles up? Does anything happen?
Doesn't change.
It's invariant with altitude, above or below. The magnitude is insensitive to that because of it's assumed infinite. And anytime you have an infinite amount of current or an infinite amount of charge, the value of the E or H field doesn't change as you move beyond. It'll change polarity to below it, or it's not, but it will not change magnitude, and that's something you have to understand. If it's infinite, keep that in mind. Because in the real world, there ain't nothing that's infinite. As far as if you're talking about proportionality, we can assume a lot of things look like infinite planes of charge or infinite lines of current or something like that, if we're close enough, but only if we're close enough. And that's a big thing to keep in mind when you're doing real world engineering. Now the next thing I want to do makes everything I just said, all these crazy integrations, go away. You remember how we started with the Biot-Savart law that the differential E field was dq over 4 pi epsilon naught r squared AR, right? That was the differential field from a differential charge. Then if you define a charge density, you want the total field, you would integrate that differential electric field over the entire volume or surface or line, right, to get the total field. And the integrations get kind of painstaking because they're vector integrals. Well, the way that we got around that was using what? Gauss's law, right? Anytime there was symmetry, we could exploit it. And you notice that all these problems we've been doing, there's a lot of symmetry. Well, Gauss's law allowed us to do simple surface integrals that we know the answer to, like the surface integral of a sphere or of a cylinder, were very easy to do. And we could get the value of the D field and thereby get the value of the E field, right? Well, now we have something that will do that for us with magnetostatics. What Gauss's law was to the Biot-Savart law, Ampere's law is to actually, Ampere's law is to the Biot-Savart law. It's actually Gauss's law is to Coulomb's law. So now I'm going to show you this. It works like this. Ampere's law. Ampere's law is one of those that I'm going to start by writing the differential form. And this is for DC currents, It means they don't change in value, they're constant. So for DC currents, you say that the curl of H is equal to J. This is the law. Curl of H is equal to J, and that's measurable, that's how it was found. Now the curl is a mathematical concept, but what we can do with this is if I go ahead and I integrate the curl of H over any, if I take this and dot it with some surface, so it's hard to render, but now I'm going to have curl of H is known, and there's a surface S here. If I integrate it over some surface, S, that's equal to the integral of J dot ds. It penetrates that surface. So if this was J and the surface had a vector sense ds vector, it would be that over the surface. Now keep watching. I don't think you had this. Maybe you did in mathematics. Do you know what Stokes' theorem is? Anybody? Well, Stokes' theorem, these are mathematical proofs, say that the integral of curl of h ds is the exact same thing as the integral of h dot dl over a contour around the contour of this surface in the counterclockwise direction. So always put counterclockwise here too, CCW. So when you're doing this surface integral, you're taking the h field in the counterclockwise direction and integrating it, and saying that integral dot dl will be equal to the amount of current, integral of j dot ds, that's penetrating the surface of this region, and that's really equal to the I that's enclosed, or the I inside that theoretical surface. Now here's how, that still doesn't mean much to you. The only thing you see is a couple of triangles and crosses, and in your mind you probably don't understand how it really applies. So I'm going to show you how it applies. First, you have to realize that there's a degree of symmetry and convince yourself out of it to use this. The simplest example of an application of Ampere's law is with a line of current. Now we know the answer to this one, but if we have current I, and call it on the z-axis here, we're just saying we've got that much current flowing up the z-axis. Let's come out a distance rho, make that a perpendicular, and say that this is my argument. I'm going to say, if I'm out a distance rho here, the magnitude of the H field here is the same as if I'm here out a distance rho, or if I'm here out a distance rho, same magnitude. Do you agree with that? Your gut should tell you yes. In fact, this, if it's infinite, if I go around it, it looks the same, so the H field has to be the same at a given distance from it. Just by basic logical reasoning, you can see it. The H field here and here, basically it's the same in magnitude, and anywhere around that loop, the H field will be the same. So now I'm out a distance rho, right? This is rho, and I can say that the integral of H dot dl around that closed surface in the counterclockwise direction would simply be equal to h phi, that's the magnitude of the H field, times 2 pi rho. Wouldn't that be the integration of that? If we assume that the H field is in fact going to be the same, and there's one other thing I got to tell you. The way you always get the direction of an H field from currents is you take your right hand, put your thumb in the direction of currents, and your fingers will point in the direction of the H field if you assume you're simply turning a door handle in this direction. Follow me? So your fingers are pointing that way. That's the direction of the H field. So that's 2 pi times rho. Now that's equal to all the current that is penetrating that surface. Can you all see how this surface is like a planar surface in the XY plane, and the current is penetrating it normal? You all see that? So that's equal to I. And that means H phi is equal to I over 2 pi rho. And that is a simple application of Ampere's law. You all see that? Now where this really is useful is, in Dr. Wentworth's book, you can't really use this much in sphericals, in spherical coordinates, because current doesn't stream radially outward very well. It does in a sense, but when it does, this is the craziest thing. I'm going to tell you this. Remember the spherical capacitor? All right, if you think about that and say allow some current, leakage current to flow from the inner to the outer radius, well, you'll notice if it's going radially outward, if you pick a point and you take a look at the differential H field in your mind, from each one of those current elements, everything cancels. And the funny thing is about a spherically symmetric current distribution, if you actually put current in to the inner electrode, you get no H field. I mean, you're going to get a little bit of an H field because there's asymmetries. Nothing is perfectly symmetric. but you virtually get no H field, which means no inductance. Now, why is that so interesting? Because spherical capacitors can discharge faster than anything. If you charge up a spherical capacitor and try to discharge it, it's only limited by the inductance of the cabling connecting it. There's no internal limits. Now, most capacitors, parallel plate, or when they wind the parallel plate to cylinders, there's an internal inductance there that limits the rate you can discharge them, but not with a spherical capacitor. The only thing that limits them are really the inductance associated with the connecting leads. And that's very, very interesting if you want peak pulse power. If you want a kajillion watts, that's the kind of thing, because watts only last for an instant, but you can get all the power out. There's other tricks too, and I'm not an advocate of spherical capacitors, because frankly, the lead inductance for the most part is what limits discharges these days. It's not the internal inductance, but keep that in mind. If you ever need a really fast discharge capacitor, use a spherical capacitor. All right, now, applications of Ampere's law. They're really to anything that looks like a pipe. And you want the H field, some thick pipe, thin pipe, a pipe with current going one way, then current going the other way, return. This is where it's used. Let's go through it. Suppose I have now a pipe, and it's got a thickness A, and it's infinite. All right, so I'm just giving you the idea. And I'm going to say that I have a current I flowing up through there. And what I want to know is the H field everywhere. My goal is finding the H field everywhere. I want to find the H field for rho less than A, and this would be, we're going to do this in cylindrical symmetry, so this would be our distance parameter rho. And I want to find H everywhere. Can you all imagine this? You got all the current flowing up this pipe, and it's infinitely long. And I want the H field. Well, the first thing I do is say, if we're at rho less than or equal to A, greater than or equal to 0, in other words, we're inside where the current is actually going, then we can go ahead and say the integral of H dot dl over the closed loop in the counterclockwise direction will be equal to the integral of J dot ds over the surface contained by it. Let me take a moment, let you write that down, and I'll try to show you how I sketch these out. I know what I'm saying is I got a surface that goes out to rho, and then I put a loop there, and all the current that penetrates through there will be used to calculate the H field at a distance rho. Make sense to everybody? All right, so if I take this up here, what does it look like? Well, it looks like, here's my big, this is at a distance A, and I'm at a distance rho inside there. And what I want to do, I know that the H field is in this direction. I want to figure out how much total current flows through there and evaluate this. So when I go ahead and I integrate H dot dl, I'll always get 2 pi rho times H feet. You remember for when we did Gauss's law, you always got, with cylindrical coordinates, 2 pi times the radius rho times the height H. You remember that for the surface? And if it was a sphere, you always got 4 pi r squared times d. Well, here, you're always going to get, for this part of the integral, 2 pi rho H feet. Now, the integral of J dot ds, it's the amount of current that's penetrating that. Really, it's a double integral. And it would be, first you'd need to find the actual current density, and that would be J, and that would be I over the area, which would be pi A squared, and would be in the AZ direction. So I would put J, or I over pi A squared AZ. And then I need ds. Well, the differential surface here, we're in cylindrical coordinates. Does anybody know what that is? We're in cylindrical coordinates, z is constant. So therefore we would have d rho, wouldn't we? And we would have, anybody?
Rho d phi.
Right, rho d phi. Rho d phi, and it would be in the AZ direction, right? And that would be, and by the way, for this one, rho would go from where to where? Now, be careful on this one. From
0 to rho.
Remember that, not A. I see 0 to 8 all the time. It's like a knee-jerk reaction, 0 to a row. And technically that means we should prime that row variable inside there. And phi goes from where to where?
0 to 2 pi.
0 to 2 pi. And that's it. And that means my h phi I'm already over. H phi would be 1 over 2 pi rho. And then there would be an I over pi a squared. And then when you do the integral, then you get 2 pi, right? And then you get rho d rho squared over 2. So then I get rho squared over 2. And that is, in fact, you can do the cancellations yourself. 2 here, pi here. I have rho squared over a squared. And it comes down to really h is equal to I over 2 pi, and then it would be rho over a squared. But that's h inside here. What about h outside? This would be that's all for for rho less than a. What happens if rho is greater than a? What do you think? Think about it. Come on, go out here and put a loop. How much current penetrates? Right, all the current, right? And I just take all the current divided by 2 pi rho. So now I can say that the H field in the phi direction is I over 2 pi rho A phi. It's just like a line at that point. Just like if all the current's on a line, an infinite line. And that's the nice thing about these problems. Now, if at some point there was a thicker pipe that had the same amount of current but in the other direction, then at some point when you get outside where that pipe is, the H field would go to 0. Right? And that would be like a coax cable effect. That's why coaxial cables don't have really any H field outside the actual outer, that woven aluminum thing. All right, I kept you over a little longer because I showed up late. I'm trying to account for Chick-fil-A and go down, not Magnolia, but what is it, Glen?
They're doing road work on.
Oh, that's right, I can't go down.